Today we start chapter 4 and section 4.1 is on related rates, and these are going to be word problems where you're going to show off your new skills at implicit differentiation. All right, so to introduce this, let's think about a circle, and let's say that this circle is growing. So maybe this circle represents an oil spill. So like there's the source of the oil spill in the middle, and it's growing and getting bigger as time passes on. Okay, so let's say that we know something about how fast this circle is growing. All right, so let's say that we know that the radius is increasing at a constant 2 inches per second. Okay, so the radius increases at a constant 2 inches per second. All right, and then let's say that we're watching this on a video, and we hit the pause button at the exact moment when that radius is 5 inches. Okay, so we're going to hit the pause button when the radius is exactly equal to 5 inches. All right, and what we're going to see if we can figure out is how quickly is the area increasing at this moment. Okay, so we have like our speedometer on the radius, and the radius is increasing. The speedometer says 2 inches per second all the time. Okay, so let's say that we managed to have a speedometer on the area, and we'll say, what does that speedometer say when we hit the pause button exactly when the radius is 5 inches? Okay, so when the radius is 5 inches, how quickly or how fast is the area of the circle changing? Okay, so let me back up to where it says 2 inches per second. So I said speedometer, so that hopefully makes you think of a derivative now. Okay, so you can think of that 2 inches per second. That's how quickly the radius is changing. Okay, so, and it looks like a velocity, right? Inches per second kind of reminds us of feet per second. So that 2 inches per second is a derivative. You might think of it as r prime. All right, for these related rate words problems, instead of using the prime notation, we're going to use the Leibniz notation. So instead of writing r prime equals 2, I'm going to say dr dt equals 2 feet per second. Not feet, inches per second. All right. Okay, and the Leibniz notation helps us to remember what our units are going to be. So dr over dt reminds us of inches over second. Radius is measured in inches. Time is measured in seconds. Okay, so then what I'm looking for, how fast is the area of the circle changing? Okay, so how fast is the area of the circle? We're going to think of that also as a rate of change. Again, a speedometer attached to the area. How fast is it changing? So we want to know how fast is the area changing, dA dt. Okay, so this is going to be measured in units of, so some number, units of area would be square inches per second. Okay, so we don't know what that is. That's what we're trying to solve. All right, so how are we going to get the relationship between dA dt and dr dt? So the way we're going to do that is we're going to start off with an equation that we know that relates A and R, and then take its derivative using implicit differentiation. Okay, so of course the equation that I know that relates the area of a circle to its radius is A equals pi r squared. And then we're going to use implicit differentiation to take the derivative of both sides of that equation. And we're going to take the derivative with respect to t. All right, because that's our variable. That's what's down in the denominator. With all your implicit differentiation homework, we were taking the derivative with respect to x, but here we're going to be taking the derivative with respect to time. So everything is dt on the bottom. All right, so both the a and the r are going to be treated like variables the same way we were treating y as a variable, like a function of x in our implicit differentiation. Okay, so when I take the derivative with respect to t of a, I might say a prime, or we'll say dA dt. And then on the right, that pi is a constant that goes along for the ride. And then we take the derivative of r squared, which is 2r. All right, but then we remember that r is changing with respect to time. So we're going to say r is a function of t, so we need the chain rule here. So in your homework, you were saying you would say 2r, r prime, but we're using that Leibniz notation. So I'm going to do dr dt. Okay, so again, that's a chain rule. Okay, so I'm going to come over to the right here and just write that a little bit more neatly. So dA dt, let's write that as 2 pi r times dr dt. Okay, so let's think about this. The dA dt is what we want over on the left. They told us at the beginning of the problem that dr dt is a constant 2 inches per second. And we also said we're going to ask this question if we pause it exactly when r is equal to 5 inches. All right, and that gives us everything we need to plug in. So dA dt is equal to 2 pi, the radius is 5, the rate of change of the radius is 2. Let's see, so 2 times 5 times 2 is 20. And then you got that pi hanging on there. Right, and that's just a number. You could plug that into your calculator. It's going to be 60-something. Pi is a bit more than 3. But we can just leave it that way, 20 pi. And that's how fast the area is changing. So I'm going to put units on there, inches squared per second. All right. And that was our first related rates problem. All right, so I'm going to post another video with a second example, and then we'll do a couple more together whenever we meet on Tuesday.